Hi, Dr. Huckabee here. This lecture is called Lecture 3.5 because it's supposed to go between 3 and 4. Somehow this clip never made it into the original work stream, but here it is. So a little more about resonance and some helpful tips in drawing those. Don't forget to finish Chapter 2, do Chapter 2 problems, and start thinking about working old exams and all the chapter problems that you can. Good luck.
And the bond line structures. Here's a double bond, here's a double bond, and here's a double bond, okay? Oh, thank you. Yeah, there we go. 3 double bonds. All right. How are you to know if these double bonds, if these molecules, these 1 propenes, have any charge? You can't, right? Because I have to give you the charges on them so that you can know which implicit hydrogens or which implicit lone pairs are there. Okay? Some books and questions will give you lone pairs, some won't, but they should always give you charge. If you don't have charge, you can't know how many implicit hydrogens to think. And you can actually make a little table for yourself. We'll do it here together so that you never get tricked on charges and implicit hydrogens. So essentially, you can boil it down to this. If you have a carbon, okay, for instance, as in our above example, you can count the number of bonds it has, okay? You can also count the number of lone pairs it has. So let's start up here at the top. On the one on the left, it has the leftmost carbon. That's the one we're going to be talking about here. The leftmost carbon in the top has how many bonds to it? 4 bonds. Everybody sees 4 bonds to that carbon? Okay, that one has 4 bonds. How many lone pairs does it have? It has 0. Good, yes. Saw lots of zeros. Nice. How many valence electrons does that carbon have? Anybody? Nothing. It's 4. It has 4 valence electrons. Remember when we were doing some structure drawing on Tuesday? This one has 4 valence electrons. Now, how many do you expect carbon to have? You expect carbon to have 4 as well. So that gives you a charge of 0. All right, and I'm actually going to draw the charge in red, just so we can see it. Okay, similarly, from the 3 examples we have up there, if you have how many bonds to this carbon now? 3. I heard a 3. That's right. How many lone pairs are on that carbon? Do you see any? I don't. 0 lone pairs. How many valence electrons does it have? It has 3. Right. We expect 4. So that means we have a charge of +1. Okay, so I realize at this moment that this should really say something like -4 plus, okay? Yeah, I think that's probably how to make this come out, right? But I think you all see where this is going. On the next carbon, it has how many bonds? Again, 3, right? 3 bonds. You can see there's a lone pair now, so that has a total of 5 valence electrons. Does that make sense? Everybody sees that? 5, because it has 3 bonds plus its own lone pair. Okay, good. I'm seeing a lot of nodding. That's good. Now, when we calculate how much charge to expect, we get a -1 charge. Okay, so that means every single time you see a carbon with a positive charge, you should know its formal charge is +1. Okay? Same with having a lone pair on it. That means its formal charge is -1. Okay, right now we're accounting for these electrons so that in the future we can know which part of the molecule will be doing chemistry that we're interested in. All right. You can do this for oxygens as well. In fact, you can do this for a variety of them, but we're only going to go through a couple. So let's do oxygen first. Let's say that you have this molecule. We'll start here. All right. This molecule is C123H36O. Okay. Does everyone see how we got C3H6O from this structure? Yes.
There's a lone pair with like 2 electrons, and why is the charge only -1?
That's a great question. So back on the last question, the last example of the anionic 1-propene, the question is, why, if there were 2 lone pairs, is the charge -1? And that's why doing this valence bond accounting, or valence electron accounting, is so important. Because if we draw this out, and I'll do this underneath it here, you have I'm not going to finish this part because it's not necessary. Okay, if you have, this is the part of the molecule we're talking about, right? So here you have 1, 2, 3 bonds. For our accounting purposes, every time you have a bond, break it in half, give 1 electron to each atom. Okay, so break it in half, each one. And now this carbon, I'm going to bring it over here so you can see. This carbon has, again, the same 2 lone pairs, 1, 2, 3, by itself. So now it has 5 valence electrons, and we expected 4. So we expected 4. We have 5. Actual is 5. 4 minus 5 equals -1. So it would have to have 3 extra electrons to come up as -2, and 4 for -3, etc. All right, so back to this molecule, which is called acetone, or 2-propenone. How many lone pairs are we supposed to give oxygen? I heard some 2s, some murmured 2s, so we're going to give some murmured lone pairs up here. All right, this molecule, we're going to look at this oxygen. What is the charge on this oxygen? Well, let's start by counting the number of bonds. Okay, the number of bonds is 2, right? Number of lone pairs is 2. The valence electrons. How many valence electrons does it have? I heard some murmurs. 6. Yes, it has 6 valence electrons. Stop me here. Shake your head, raise your hand, whatever, if you don't see 6. Okay. Good. So how many do we expect? We also expect 6. Oh no, I did it backwards, right? Minus and plus. So that means we have a charge of 0 for that oxygen. Now, what about this structure? Okay, this structure is now C1234 H369O. Okay. Am I missing any lone pairs? Yes, I'm seeing some nodding heads. Yes, we're missing 1 lone pair. I saw a number 1 come up. Missing 1 lone pair. Okay, what is the charge on this oxygen? If we go through our standard set of questions, how many bonds does it have? It has 3 bonds. How many lone pairs? It has 1 lone pair. That means we have how many valence electrons? 5. Yeah, I heard it better that time. 5. Okay, we expect 6. Minus 5 plus 6 is a +1 charge. Everybody see that? Okay, good. Because we're going to do a very similar thing for this molecule here. This molecule is C123, okay, C3, H3, 6, O. Okay? Now, I have given you no charges, so I should do that. Oh, I should have done it here too. That was a dirty trick. I'm sorry. I apologize. In this one, there's a positive charge on the carbon and a negative charge on the oxygen. How many lone pairs am I missing? 3. I heard it. Okay, 3. Good job. 3. 1, 2, 3. Great. What's its charge? We go through the same exercise. It has 1 bond. It has 3 lone pairs. We expect 7 valence electrons. We expect 6. We get a -1 charge. Okay? So now, if you ever see oxygen with 3 bonds, what are you going to think? It has a positive charge. Even if for some reason the charge isn't given. That's what you're going to think. Same for 1 bond. Oxygen with 1 bond, you should assume has a negative charge. And you should be able to work it out using the same logic. All right. So last, and maybe a little faster, since we've gone through 2 examples of this now, is nitrogen. Nitrogen, another one that we'll deal with a lot in this course, does the same thing, just in a slightly different way. So here, we have nitrogen. You don't have to, sometimes the books are a little weird with how they draw nitrogenous compounds. You can have it in this structure, or perhaps you have it in this structure. They're the same. Okay? Go down again. Oh, thank you. Feel free to say something if I'm not looking up. All right. Am I missing any lone pairs for this nitrogen? Let's just focus on this one on the right here. Am I missing any lone pairs? Yes. Good job. Missing 1 lone pair. Okay, what is the charge on this molecule, or on this nitrogen? So go back to our, where is that? Here you go, I'll put it behind. There we are. Okay. Yeah, now you can see that. Okay, how many bonds does it have? It has 3 bonds. How many lone pairs does it have? It has 1. How many valence electrons do you expect from that arrangement? 5, right? Stop me if you don't see 5. Yes? Okay, 5. We expect 5, so the charge is 0. All right? Similarly, nitrogen. In this case, am I missing anything? I am. I'm missing a positive charge. And the formal charge on this nitrogen with 4 bonds, 0 lone pairs, and 4 valence electrons is +1, right? We're all seeing this. We're all on the same page. Okay. It's really lonely to be the captain on a ship of 1. All right, last, just to be complete here, we have a nitrogen with only 2 substituents. Substituent is another word that you'll use a lot in organic chemistry. That just means something bonded to it. This has 2 lone pairs because it has a negative charge, right? And its formal charge is going to be, after having 2 bonds, 2 lone pairs, and 6 valence electrons, we expect 5 and get a charge of -1. Okay. Hopefully, you have recognized the pattern here. Organic chemistry is, in a lot of sense, recognizing patterns. So, these are going to follow a pattern that we're going to see for this whole semester. So hopefully you can stick this in your mind now that we've gone over it pretty early and use this as we go. Right, all right, so just for fun. This means I could probably draw you something crazy, and you could tell me what all the charges are, right? Like if I just went really out of the box and just gave you something that looked like this. Oh, that's 5. That's bad anyway. You could pretty well see what the charge is on this, right? You hold up a finger. No? Nitrogen, minus, plus, nothing. All right, so the minuses. Formal charge of -1. Anybody think it's that? What about +1? Raise your hand. Yeah, good. I see a lot of hands. Good. So then you probably all see what the formal charge is here. All right, good. I'm glad to hear that. But I did give you the charge. So just for your own understanding, could you do it without? So let's try one, right? So let's do this. This molecule has an oxygen, has a nitrogen. Who thinks the formal charge on oxygen is 0? Raise your hand. Totally neutral? No? Who thinks it is a positive? Okay, we got some. What about negative? Negative on oxygen? Okay, that one is positive. Why? 3 bonds. Oxygen is bad with 3 bonds. Bad because it has a charge. It's also not neutral with 1 bond. So you'll start to get these to stick. What about the nitrogen? Who thinks it's a positive charge? Anybody? Okay, good. What about negative? Yeah, look at all those hands. It's a negatively charged nitrogen because it has 2 bonds. Again, don't be too upset if you didn't see it. We'll do this together a lot. You will learn them. All right. Now, let's go back to a fun example that we all enjoyed, and that is one propene. Okay? Except, we're going to make this even better, and we're going to call this by another name, and that is the allyl cation. Okay, this particular functional group, one propene with a cation on the 3 position, that's just called the allyl group. It's like a common name that they came up with a million years ago as well, and it stuck. So we call this an allyl group. It is a cationic allyl group, and we call this an allyl cation here in this position. This is also a carbocation. Can you imagine why it's called a carbocation? Because it's on a carbon, right? Exactly. Now, we're going to use this to go into resonance because if you remember from the last class, this carbocation is actually on a pi bond, right? It's actually on a pi bond. So if you have this pi bond and this pi bond, why wouldn't they interact? They're the same phase, right? It's just that one doesn't have electron density and the other 2 do. In fact, they do, and you can do the same type of molecular orbital analysis that we've been doing to talk about where those electrons might actually be in the molecule. Okay? So if you remember back to regular double bonds, regular carbon, carbon. Okay? Remember we said that had a highest occupied molecular orbital and a lowest, right? It was the highest occupied was here, and the lowest had a different structure. Now let's keep these open. And the difference there was the constructive and destructive interference, right, between the 2. Either you had a bond between or you didn't. So we'll just draw a line through. Okay? It turns out you can do a similar analysis with 3. Okay? You have, instead of 2 energy levels, because you had 2 orbitals you were talking about, now you're going to have 3. And that's because, again, you have to have the same number of orbitals out that you put in. Okay? To make it a little easier, I'm also going to draw the shape of the molecule beside them. So what do you think would be the lowest energy, the most stable version of this molecule? Is it going to be the version where you have a lot of destructive interferences, or is it going to be the one where you have a lot of constructive interferences? The second one, right? They're all happy. Everybody is working together. So we're going to do that. All right. And what about the least stable? the highest energy, the one that the molecule is, the least happy to use, what do you think that's going to have? You think it's going to have the most destructive interferences? You think it's going to have any overlap between the orbitals? No, I'm seeing some shaking heads. All right, some people are here with me. That's right. So you can, just like a wave diagram, just like I don't really know how to make the analogy of this very second, but you can construct a version of these three atoms, these three pi orbitals, where you have no constructive interference between either of them. And we'll just draw a line through them so that you can see there's no bonding in between. But what about that second one? Right? We have 2 electrons, so we know automatically from our last lecture that they're going to be filled in the bottom. So we know the molecule is pretty happy. We know where the highest occupied molecular orbital is. But what about the middle electron? That's our LUMO, that's our lowest unoccupied. It's also very important for chemistry. What are we going to do there? Let's start by drawing these 2 here on the outsides, and we'll give them the same phase. Okay, we know that if we give the middle one the same phase, it's going to be the HOMO, and we know if we give the middle one the opposite phase, it's going to be the highest energy orbital. So we really only have one option here, right? And that is that the middle one has no electron density. It's called a node. And it may look really weird, but it makes sense if you think about electrons as being both particles and waves, okay? Because in this bottom example, the wave extends over the whole molecule, right? And in the second example, the wave comes here and crosses over one time, and in the third, it crosses twice. Okay, so pretty confusing, pretty weird, but electrons are confusing and weird. So that part makes sense. So now we've drawn what the frontier orbitals look like, but that doesn't really tell us anything, right? Like we have it there. What we really want to know as fledgling chemists, biochemists, doctors, is what does this mean about the molecule? Like what can we say about it? You need to put all of these 3 structures together, and you need to assess if they contribute to what you can really say about the molecule. Remember at the beginning, we had the methyl isocyanate, and I was talking about how they kind of come together, and you have to compromise the 2 structures. Well, you kind of do that here as well. So, bless you. Let's draw our first one, this cation here. All right, I think it's safe to say we could draw another structure that is exactly the same, like this, right? You can imagine if you flipped one over, it would just be that other structure, okay? But we could probably also draw a really weird one based on that second energy level, 2, where we have no electron density and we have a couple of electrons on the outside, okay? Can you look at these 3 and find which is the bad one? There's one that is just crazy. Yeah, it's the one all the way over on the right. This one, while maybe we can draw it that way, is horrible. That doesn't contribute at all to what the molecule actually looks like. So that means we put together the other 2, and they together will average out to what the molecule actually does and what it actually can be described as more accurately. I'm going to draw it actually over here since I have space, right? So let's start with the one on the left. We'll draw it here. And we'll have the other one on the right. We'll draw it down here. Resonance, which is how we came into this small section, is how you describe the 2, these 2 different structures. Because resonance means that you're constantly interconverting between each of these. because we're viewing these on paper, we're drawing them, we can only really do as good as saying they are constantly intraconverting, right? And we do that by putting brackets around them. This is vertical, so I'm going to draw vertical brackets. You can draw horizontal as well. It's the same. Okay, and to do this, to show that they're intraconverting, you use a double-headed arrow to show where the electrons are going. Okay? Now, please note, I have been very specific about this arrow, because this is your third lesson on how to speak OChem, how to draw arrows. This is seriously the number one best way or worst way to communicate what you're trying to say about a reaction or about a molecule, is by getting the arrow wrong or putting it in the wrong place. A double-barbed arrow says 2 electrons do something. Okay? If you draw a singly barbed arrow ever, that means 1 electron is doing something. This is the equivalent of saying the double-headed arrow tells you from the structure on the top, you get the structure on the bottom because both pi electrons are formally on the other atoms. Do you all see that? Okay, I'm going to draw you what the opposite situation is. Okay, this is just for an example. We probably won't even talk about this in really big detail later, but it's the best way. So if you see your notes later and you're like, what even is that? I hope you can remember this moment. A single-headed arrow tells you something totally different. Do you see that? If you draw a single-headed arrow, this is what the person looking at what you're trying to communicate will think you meant. And I don't think it will be. So please remember double-headed arrows. Also, the double-headed arrow needs to go to the bond in a resonance structure. Okay? Good resonance structures. Let's say you have this molecule. Okay? Negative on top, positive on bottom. A resonance structure of this molecule might be like this, where the electrons on the oxygen now form a pi bond between the oxygen and carbon. And we draw brackets to signify that. Bless you, I think. Now, I hope you all see that I very specifically pointed to the middle of this bond. Okay? Again, we're talking about communication, about electrons. If you draw this, to me, and to anybody else who can read organic chemistry and speaks it as a second language, you have meant this. Okay? There is a difference there. Because sometimes, in more complicated examples, you do mean something like that. Similarly, if you draw it onto the oxygen, then you're saying, like, I don't know, the oxygen is superpowered or something. You want to draw it into the middle of the bond for resonance, okay? Double-headed arrows, in the future especially, will be where you make your most points on tests. Also, maybe where you lose the most partial credit on tests, because somebody grading can't say that you are communicating effectively what you mean if you don't draw the arrow in the right place. Okay, so hopefully I've hammered that enough to where you will try to remember that. Some other accounting things, you might remember from Gen Chem, equilibrium arrows, less of an issue right now. We talked about the forward arrow, something goes to something else. And then the two types of equilibrium arrows where you have one really big one, one small one. Hopefully that's relatively straightforward. If it's not, we'll cover it later when it's a little more topical. But I figured I would show you like all the types of arrows you might encounter. Okay. Right. Oh yeah, so back before I went on my tirade about arrows. All that resonance business with the allyl cation to say that you can either show a resonance form, or in some special cases, you could show this type of structure, where you try and show that electrons are, there's like a deficiency across the whole thing, but it's not really a great way to communicate it. It's much better to say resonance structures are intraconverting. Okay, that way you are clear what you mean, and so am I. All right. That was what I wanted to touch on for allyl cations, and I have my tirade about the arrows. And now we are going to talk about some handy tips for making resonance structures. Because we talked about what they are and what they represent, but there's some things you can do each time to make sure that you're at least thinking the right way. So, rule number 1. It's a very short list. Rule number 1 is never, and I mean never, when you're drawing a resonance bond or a resonance structure, break a sigma bond. What's a sigma bond? A single bond between carbons. A single bond between anything. Only pi electrons can be moved in a resonance structure. Okay? Hopefully you remember what a pi electron is. Pi electrons are double bonds. So that means, in that example we were just talking about, again, to go back to that, we had 3 p orbitals, 1 pi bond. The electrons inside of a pi bond are what? Pi electrons. They can move. Never break sigma bond. There we are. Pi electrons can move. What can never move, for instance, in this example, so you had this molecule, this butene, this one butene cation here. What can never happen is breaking a bond to make new chemicals like this. I guess that would be a positive there. Okay, that's clearly now 2 new molecules you've made. And you're not talking about 2 molecules, you're trying to describe 1. You're trying to use pi electrons to describe 1 molecule. So never ever break a single bond. If you feel like you're about to break a single bond, stop and do something else instead. Okay? Now, number 2 is always obey the octet rule if you can. You're going to see, as we move through talking about resonance structures, that it's all about comparisons. Which structure is better than others? So here, obeying the octet rule if you can really makes a difference. Okay? For instance, I should probably write it down. Remember octet rule. For instance, let's say you have this molecule. Okay, this one is, oh, there's a negative charge here. So now you have all the information. This molecule is C123 H347 O. Okay, this molecule has how many lone pairs? 3, they said? 3 lone pairs. A good resonance structure is not possible here. Does everybody see why before I draw it? If not, here it comes. Those lone pairs coming down here are not allowed because of this hydrogen. Okay? If you move those lone pair electrons in between the carbon and oxygen, you will make 5 bonds to carbon. Carbon hates 5 bonds. Never do that. So you cannot use that resonance structure here. On the contrary, you can't have so you can't have more than an octet, right? That's the rule. That should be the rule. Never have more than an octet. But you can make less than an octet. We've already talked about. Sorry about that. We've already talked about one very good example of how you can have less than an octet. But you can do that all the time in resonance structures. For instance, go back to a molecule we talked about earlier, acetone. It's fully neutral. The molecule is C123, H36, O, and there are 2 lone pairs here. A valid resonance structure for this molecule does exist, and it forms by moving these pi electrons to the oxygen to make the oxygen still has its octet, it's still happy, but the carbon doesn't. We could talk about the math behind this for the next 3 hours, but let's just boil it down to carbon is fine having a positive charge if the pi orbitals allow it. In this case, we took the electrons straight out of the pi orbital and onto the oxygen, and the carbon's fine with that for this resonance form. It doesn't really say at all if carbon is happy with that situation, but carbon is fine with it. It'll allow us to draw it that way. But when we think about this molecule, acetone, you never think about this. It's a bad resonance structure. It's valid, but it's not as good as the first one where all the atoms are neutral. I've shown you pretty simple examples where you can have, one arrow pushing that gives you a different resonance structure. But as you can probably expect, they could get very much more complicated. For instance, a more complicated but still pretty simple example is here. We need to keep rules 1 and 2. Never break a sigma bond. Never exceed an octet, right? So what options do we have? We have a pi bond, and we have a lone pair on nitrogen. Who here thinks we have more than 2 pi electrons to work with? More than 2 pi electrons, or less than 2 pi, or just 2 pi electrons? All right, pi electrons, 2. Raise your hand. We got 2, more than 2. You're all still with me. We're almost there. We're almost to the end. This is the last thing we're going to cover. This molecule, in fact, has 4 pi electrons. Yeah, it's unfair as well. It doesn't actually have 4 pi electrons, but in organic chemistry, you treat nitrogenous lone pairs as pi electrons, exactly like we did those oxygen electrons. You remember I kind of skirted past that? Yeah. In the same way, with the oxygen lone pairs, we were just throwing them around. It didn't matter. Heteronuclear meaning just not carbon. Any lone pairs on something that isn't carbon can be treated like a pi electron, just about. There are some exceptions, as always, but they can be treated like pi electrons. Yes? No? In the back? Yeah? Okay. Good. Well, that was exciting. All right, so what this means is this is the technical difficulty part of the question. So what this means is that we can move either this pi electron over and generate a structure looking like this. And resonance structures, you also show the backward motion of how to get there. Okay? Or we could do something like this. Let's draw this molecule out again. You could do 2 arrows to get you the same place. But you have a vastly different structure, because in the top one you had a separated positive minus on adjacent carbons, and here you have a larger separation. Now, to hopefully cement into your minds that resonance means something in organic chemistry, besides just drawing bonds on a piece of paper, you all need to know resonance structures are the cause of why our bodies. Is this on or not? I don't. No. Yeah, that's annoying. Resonance structures are the reason why we have are held together by peptide-peptide